Okay, let's start with the last lecture of the school, which hopefully will be more inspirational. Hear about OP of the light race operators.
Okay, this talk will be a continuation of Andrea's talk from just before. No, I'm kidding. We're going to switch subjects and continue talking about light ray operators. And so last time we wrote down this object that has two nice properties. One is by construction, its residues are equal to light transforms of physical local operators in the theory. And two, it's analytic in J. So this object encodes an analytic continuation of OPE data. And so we saw before another analytic continuation of OPE data, which was Karen-Ho's formula. And so now I want to relate these two objects to each other. So the way to do that is to just ask, what is a matrix element of one of these light ray operators? And this question is going to lead us naturally to a proof of Karen-Ho's inversion formula. So we're going to study a matrix element in states created by primary operators phi 3 and phi 4. And okay, so we just plug in this formula here. It's this integral over some particular domain, dx1, dx2, of now a 4-point function, the physical 4-point function, against this funny kernel, which we got by taking the standard CFT 3-point structure and light transforming it. Okay, so let's draw a picture. So I'm going to consider the configuration of points where 4 is here and 3 is here. In order to get a non-zero matrix element, we have to have our light ray operator cutting between them. That was this result that we saw last lecture. So I'll put x here, and our light ray operator will be living on this, this light ray. And then the integration region here is telling us that the light ray splits space into two regions, and one has to lie on one side of the light ray and 2 has to lie on the other. Okay, so 4 and 3 are fixed, and 1 is being integrated up here, and 2 is being integrated down here. Okay, so that means that we can use a little bit of information about the ordering of these operators and write this correlator in a particular way. So it's a time-ordered correlator of phi 4, phi 1, and then time ordering of phi 2, phi 3. And we can do this because this pair of operators is guaranteed to either be in the past of or space-like from this pair of operators. Okay, so now we're going to do a couple quick manipulations that get us to Karen-Ho's formula. And the first one that we have to do is to explain the appearance of the double commutator. So the idea is that, so we're integrating 1 and we're integrating 2. And let's just think about doing the integral of 1 over a null line first. So we're going to integrate over this null direction first, and then later we'll integrate over the other directions. So now, if we imagine instead doing the integral, so I'm going to subtract from this the integral where phi 1 acts on the vacuum. So this is a particular choice of ordering. Then, okay, so we're doing the integral over a null line. But here phi 1 is acting on the left vacuum, and this other thing that depends on on x1 is also acting on the left vacuum. And so therefore, this whole integrand, that is this thing times this thing, is holomorphic in the lower half plane, in the V parameter along this light-like line. Okay, so now I'm quoting a result from our proof that the light transform kills the vacuum. I'm just using the same argument. So let the distance along this light-like line be V1. The claim is that if we look at the V1 plane, then we're doing an integral like this, and there's a region of holomorphicity in the lower half plane. So provided we can get some control over the behavior at the ends of the integration, we can deform the contour into the lower half plane to get 0. Okay, and so you can argue indeed that you have good enough fall-off condition at the ends of the integration. So that means that this contribution is just 0, and so I'm free to subtract it. But now, if I have this time-ordered correlator, and I subtract a particular ordering, then if, let's see, so if 1 is in the future of 4, then this is 0. And if 1 is space-like from 4, then this is 0. It's only non-zero if 1 is in the past of 4. And in that case, it's equal to a commutator. So another way to write this is that this is phi 4, phi 1 times a theta function that imposes that 4 is in the future of 1. So it means that instead of integrating 1 over this entire region, now after subtracting this term that's equal to 0, 1 is stuck in here. In this small region. And there's a similar, so we've replaced this product of operators, phi 4, phi 1, with a commutator. And there's a similar manipulation that you can do for phi 2 and phi 3. So if we subtract the term where phi 2 acts on the vacuum, then this is mostly 0 except where it's equal to a commutator. And we get a theta function that imposes that 2 is in the future of 3. So now we can modify this picture again. And 2 is up there. Okay, so that means we can subtract another term and add another term. We have 4 terms, and most of them are 0. And the end result is that we turn this time-ordered correlator into a double commutator. So, let's see. Okay, so let me write again now what we have. This is now equal to an integral with some interesting causal relationships. So now 1 is restricted to be in the past of 4, and 3 is in the past of 2. And I guess I wrote this, right, so 3 is in the past of 2, and previously I was writing that x is bigger than 2 minus, and here I rewrote this as x plus is bigger than 2. So remember, these minuses and pluses are just taking points and shifting them to the next Poincare patch. So when I shift both the points, it doesn't change the causal relationship between them. So I just wrote this in a different way. Okay, and so we have the integral dx1, dx2 against this double commutator. And then our light transformed 3-point function. Okay, so this formula already is pretty nice, and the reason it's nice has to do with the positivity properties of the double discontinuity, this double commutator. So we did a calculation a while ago where we computed the double commutator in terms of cross ratios. We plugged in some conformal blocks, and we found that you got positive factors inserted in the conformal block decomposition. And that positivity can be generalized. There's a statement of Rindler positivity, which is essentially a statement that correlation functions, appropriate correlation functions that are Rindler symmetric are positive. And this is an example where we have a sort of Rindler symmetric configuration. By the way, when Rindler symmetric, I mean if you apply CRT, the CRT operator that Tom defined, to these operators, and you take these operators, you take the correlator with their CRT images, then the claim is that's supposed to be positive. And so we have some kind of Rindler positivity here, which is related to the positivity that we observed in the conformal block decomposition for this thing earlier. So it means that we've expressed these matrix elements in terms of an integral of something positive. And this positivity is enough to recover another proof of the Anak by Hartman et al. So this is essentially their proof, but in slightly different language. The idea is that, so when we set delta equal to d and j equal to 2, then this becomes the Anak operator. And this is a formula for matrix elements of the Anak operator. And it's a formula that involves the integral of something positive against the integral of something that you can check to be positive. We have to be a little more careful. So actually, the Anak operator is a residue of this thing. So what you need to argue is that this function has the right sign such that when you take a residue at delta equals d, then you get a positive residue. Okay, and under some technical conditions, you can argue that this is true. And so this gives another way of seeing the average general energy condition that on the face of it looks just like completely different from the way you saw earlier today. Okay, so this is starting to look a little more like Karen Ho's inversion formula. But it's a little weird because it doesn't have any cross ratios in it. It's just the integral of a 4-point function against a 3-point function. And so the next step is to manipulate it to turn it into something where we see the funny conformal block from Karen Ho's formula appearing. And the first step for that is to notice that the left-hand side is fixed by conformal invariance. We just have a 3-point function of 2 scalars and an operator with spin j. So it's fixed by conformal invariance up to some constant that I'll call c of delta j. So c plus minus of delta j times something that transforms in the right way under the conformal group, and that would be the light transform of the standard conformally invariant structure. Okay, so this again, because this 0 means that it's this isn't a real correlator. This is just a function. This is the unique conformally invariant function for these representations, and the dynamical information is all in this coefficient. So what we'd like to do is write a formula for this coefficient, and we have the double commutator there, so it's looking pretty close. And the thing that we need is to find some way to isolate this coefficient. So we're going to define some kind of dual object and a pairing such that when this dual object is paired with this 3-point function here, then we get 1. And I'll put an L subscript on this thing to indicate that it's a Lorentzian pairing. Now, we already talked about 3-point pairing earlier. Probably most of you don't remember, but on Monday we talked about an example of a 3-point pairing in Euclidean signature. And the idea for these Lorentzian pairings is it's almost exactly the same. But we need to tweak things a little bit. So the idea with this 3-point pairing, so recall that there's this observation that if you take an integration measure, an operator with dimension delta, and let's give it some indices, and some shadow operator with dimension d minus delta, also spin j, then this combination together transforms like a dimension 0 scalar and therefore can be integrated in a conformally invariant way. And then the idea for the Euclidean pairing was to just use this pairing separately on all 3 operators. And you have to divide by the volume of the conformal group to get something finite. So we can almost just do that here. We have a 3-point function. We're trying to pair it with another 3-point function. But the problem now is that this 3-point function involves one of these continuous spin operators. So we need to upgrade this thing to work with continuous spin. So this pairing will work fine for the scalars here. So we have phi 4 and phi 3. Those are scalars. So this thing is going to transform, well, it's going to have something that transforms like the shadow of phi 3 and the shadow of phi 4. And those are going to be fine. We can just use this pairing. But for the continuous spin thing, we need a souped up pairing. So the idea is to integrate over both x and z. So we're going to integrate dx. And then how do we integrate dz? So z, we just integrate dz, but z is constrained to be null. So we have to stick in delta of z squared here. And furthermore, z is a projective variable. It's everything that we are dealing with is homogeneous in z. So if we're going to get something finite, we're going to need to divide by rescalings of z. So this is another one of these integrals that you have to gauge fix. We'll divide by the volume of rescalings of z. And so then what can we do? We can have O of x comma z. And this can be paired with something that I'll call OS of x comma z. Just to make this pairing conformally invariant, we now can read off what the quantum numbers of this thing have to be. So OS has to have dimension d minus delta for the same reasons as before. And now for the spin, we want the measure times this product to be degree 0 in z, so that rescaling of z becomes a gauge symmetry of the integral, and then we can divide by the volume of that gauge group. So this thing has homogeneity j in z, and this thing has homogeneity d, and this has homogeneity minus 2. So this thing has to have spin 2 minus d minus j. So there's a natural Lorentzian pairing between things with dimension delta and spin j, and things, something with these quantum numbers. So this means that this dual guy has to be proportional to a 3-point structure that contains some the shadow of phi 4, and then some continuous spin operator with dimension d minus the dimension of this, but the dimension of that is 1 minus j, and spin 2 minus d minus the spin of this thing, but that's 1 minus delta. So maybe your heads are spinning with all of this. Okay, and so now let's do some simplification. So this is j plus d minus 1, and this is delta minus d plus 1. And those of you who, yes?
Sorry, this may be a silly question, but how do you define the shadow transform in Lorentzian signature? Is it exactly the same, or are there any subtleties?
That is not a silly question at all. So in Lorentzian signature, there's actually sort of a zoo of conformally invariant integral transforms. So there's one analogous to the shadow transform, the Euclidean shadow transform. It's what you get if you take the Euclidean shadow transform and you Wick rotate it. So there's that. But there's also a continuous spin version of the shadow transform that actually acts like this. Instead of just flipping delta, it flips this whole thing. There's the light transform. And actually, there's a whole algebra of integral transforms. There turns out to be like a dihedral group worth of integral transforms, and they interplay with each other in an interesting way.
So which one of those is phi tilde in that expression?
Which one is phi tilde? So what I mean here is just write down the standard three-point structure and make the replacement delta 1 goes to d minus delta 1. That's what this notation means. So it's not a transform. Other questions? Okay, so those of you who are still awake might recognize these numbers as being the funny quantum numbers in Karen-Huo's formula. Okay, so we're actually almost there. Let's see. Good. So this Lorentzian pairing just uses these pairings that we found before, the integer spin pairing for the two scalars and the continuous spin pairing for the continuous spin thing. And just for completeness, it looks like this. So we take a product of objects that transform in the indicated way. I'm not being precise here about what objects they are, but just things proportional to CFT three-point functions that transform in this way. And we take their product and integrate over all points. Divide by the volume of the Lorentzian conformal group. And we also integrate over Z. And this capital D, d minus 2z, is this funny measure that I wrote down just before. Okay, and then we just take the product of these things. Okay, so we take this Lorentzian pairing and we apply it to both sides of our equation. On the left-hand side, we get a constant times C of delta J. So this will give us a formula for C of delta J. And on the right-hand side, we have a bunch of integrals to do. So this pairing is going to introduce now an integral over 3 and 4. We already had an integral over 1 and 2. So overall, we end up with an integral over all the points. And I'll single out the points in the 4-point function, divided by the volume of the conformal group, times the double commutator, and then the remaining integral is the integral over x. So, and we have some various causal relations between everything. 4 is in the future of 1, 2 is in the future of 3. And then x is constrained to be between 1 and 2 minus d dx, d minus 2z, phi 4 tilde, something with these quantum numbers. Phi 3 tilde times our light transformed 3-point structure. And then there's another term that I'm not writing with 1 goes to 2. And the final claim is that this thing is just Karen-Ho's conformal block, this integral. And in fact, this is a famous formula for a conformal block. And I'll try to make that clear in a moment. This formula for a conformal block goes back to Polyakov's original paper on the conformal bootstrap. Let's see. So we're going to try to argue that this is Karen-Ho's block, this thing right here, and then we end up with an integral of Karen-Ho's funny block against the double commutator. It looks a little different because before we wrote this integral in terms of cross ratios, and now we have it as a space-time integral. But the way to go between those things is to take this space-time integral and gauge fix it. So you gauge fix 3 of the points to be at 0, 1, and infinity. The 4th point is at some cross ratios, and that's how one gets to Karen-Ho's formula. So now I'm just going to argue that this thing is a conformal block of the right kind, and that'll establish what we wanted to prove. So the idea is to look at this sort of dizzying array of causal relationships that we have. So here's 4, here's 3. Let's see. X is here. 1 is here. And 2 is here. There's a trick, which is that conformal 3-point functions only change by a phase if you take objects in those 3-point functions and move them to their image points in other Poincare patches. This is actually a nice trick for figuring out how things behave in various limits. Basically, you should check this for yourself. If you take the standard conformal 3-point function with any quantum numbers in it, and you move points to their image points, in the embedding space that just corresponds to taking the embedding space vector to minus the embedding space vector, you just get phases. Various phases that depending on the I epsilon prescriptions, but you just get phases. And so we're just going to try to analyze this thing up to some, I'm going to ignore the phases. I'm not going to worry about constant factors up front. So the argument is as follows. So why is this thing a conformal block? Well, first of all, it's a conformally invariant integral of 2 3-point functions. Therefore, it behaves like a conformal 4-point function under conformal transformations. Second of all, it's an eigenfunction of the conformal Casimir equation. The reason for that is it's actually an argument that we used a few times, a few lectures ago, which is that if we hit this thing with the conformal Casimir operator, let's say acting on points 1 and 2, while keeping 3 and 4 fixed. So we hit this thing with the conformal Casimir. Now, this thing is invariant under conformal transformations of all the points. So if we act on 1 and 2, it's the same as acting on O. So we pick up the conformal Casimir of L of O. But L is a conformally invariant integral transform. It preserves the Casimir eigenvalues. So that's the same as the Casimir eigenvalue of O. Okay? So this thing is an eigenfunction of the conformal Casimir. And therefore, the whole integral is an eigenfunction of the conformal Casimir. So now we know that it's a conformally invariant 4-point structure that's an eigenfunction of the Casimir. That means that it's all we need to do to figure out what conformal block it is study its OPE limit. The OPE limit will give us the boundary condition when 2 points approach each other, and that is sufficient to determine the conformal block. So we're going to try to study this OPE limit, and we're going to use this trick where we take points and move them around to different patches. And so the first thing I'm going to do is take 2 and move it down here to this patch, to 2 minus. Then I'm going to take 4 and move it down here to this patch, which is actually the same one as this one. Remember, these guys wrap around on the cylinder. So 4 is going to be down here somewhere. And so now we have the following type of integral. We have, let me just redraw it over here. So after making these replacements, we have 1, 2 minus, a diamond, and x is in the middle. And then we have 3 and 4 out here, 3 and 4 minus. And now the idea is to study this OPE limit where 3 and 4 approach each other. So this integral over x is in this region near 1 and 2. It stays away from 3 and 4. And so it means that we can take the OPE inside the integral and there won't be any problem. We can study the OPE limit directly inside the integral. I'll say for a moment why we need to worry about that subtlety. So we just have to take the OPE of 3 and 4. So then the structure of the whole thing is determined by the structure of this OPE. And the 3 and 4 dependence is in this 3-point function. And so we're going to get a conformal block with these quantum numbers. So here's how the argument would fail if we try to do it with looking at this limit. So if we take the limit of 1 and 2, the problem is that this point x is probing this neighborhood of 1 and 2. So doing the 1, 2 OPE inside the integral is not going to give a good answer. It really depends on the full structure of the integral. And you can see that if you try to do the 1, 2 OPE, you would conclude that this thing has the wrong quantum numbers. You would conclude that it's a conformal block for these light transformed quantum numbers, which isn't the right answer. So instead, you're supposed to take the 3-point function where the integration point is staying away from that 3-point function. And if you like, you can sort of think of it as being like, well, the integral is just kind of producing some stuff over here. So in the limit where these points are really close, I can imagine that all of this stuff is really far away and treated as some just effective operator. And you can argue that that operator has to have these dimensions and spins. Okay? So it means that this thing here is precisely this funny conformal block. And this, yeah, as I said before, this formula for a conformal block as the integral over a diamond in Lorentzian signature was in Polyakhov's original bootstrap paper and is a really useful thing to know and has lots of nice applications. Okay, so that's it. That's the proof of Karen-Ho's formula. Any questions?
Why was it useful for Polyakov? How did he derive this one?
How did he derive it? Yeah, well, I don't remember. I mean, that paper is incomprehensible. I'm not sure. I mean, I guess, you know, there's a simple symmetry argument. The one I just gave, based on the Casimir equation and the behavior of the OPE limit. I don't know if that's what he had in mind. I mean, who knows what he's thinking. Yeah. Other questions? Okay. So this, okay, it may have seemed like there were a lot of steps and a lot of weird ingredients, but I wanted to present this proof to give, well, for two reasons. One is that once you know that these light ray operators are there, once you know that you should think about this structure, then this formula kind of falls out. I mean, you need to know you need to be looking for funny pairings like this, but we didn't really have to do a lot of work in the end to get this formula. Maybe someone's disagreeing, but it really comes from deciding to look at the matrix elements of these things. There are other routes to proving this formula where you just feel like you're fighting, you know, the whole way. And I think this is the right way to think about this formula. And as evidence for that claim, I want to do now an application of light ray operators, a slightly different computation where we'll see that you basically just have to follow this logic again and you get an interesting result. Okay? So that's the next thing I want to talk about, an application of these funny light ray operators. And the application comes in studying a kind of OPE of more traditional light ray operators. So I should say what I'm going to present now is work in progress with Sasha and Peter Kravchuk and Murat Kologlu. So we're going to ask a seemingly simple question, which is what happens if you have two Anak operators on a null plane? So not one Anak operator, but two. And I'll ask this question more generally about null integrals of any two operators. So these operators are going to sit on the null plane u equals 0, integrating them in the v direction at some transverse positions. So here's one of them. Here's the other. And the question we're going to ask, so here, the picture is this. Here's a null plane, and we're integrating these two operators along the null plane. And the question we're going to ask is there some kind of operator product expansion in the transverse directions? Okay, so we have a transverse RD minus 2. So these yi's are in RD minus 2. And these null integrated operators are point-like in that transverse direction, and so it's natural to ask if there's some kind of expansion as these points go together. So we can kind of guess what this expansion looks like just from dimensional analysis. We have y12 to some little delta, which will be the dimension of the thing appearing in this OPE, and then we need to subtract the dimensions of these two guys. And they're one-dimensional integrals, so this guy has dimension delta 1 minus 1, and this guy has dimension delta 2 minus 1. And then the question is, what goes here? So I'm going to talk a little bit about the symmetries of this situation and try to convince you that, that this question is interesting because there's something a little weird going on in this product of operators. And of course, you'll probably be able to guess what the resolution of the weirdness is, but let me try to establish the weirdness first. First, let's use some of our technology to understand what this is a little more invariantly. So you probably recognized that this is a product of light transforms. These light transformed operators, remember, it's very useful to label them by the initial point x and the null direction z. So we can ask, what's the initial point here? Well, the initial point is some point at past null infinity. And it's the same initial point. Here's another way to draw this. This thing looks like we have some point x at past null infinity. X is somewhere down there, and we have two operators coming out of x with different null directions, z1 and z2. So this picture here, where we have these two null directions on the null cone, is conformally equivalent to this picture here, where we have two parallel lines on a null plane. So what we're really studying here is the light transform of O1 at x comma z1 times the light transform of O2 at the same x and with a different z2. And the relationship between, so these y's were in Rd minus 2, and these z1s and z2s, they're null vectors in Minkowski space. And there's something kind of cool that goes on here. So you can think of Minkowski space as the embedding space for Rd minus 2. Right? So the way we got to the embedding space from Rd was we went from Rd to Rd plus 1 comma 1. So this is the same thing. We're going from this to this. So these are two different ways of looking at the same space. So these are like embedding coordinates. For d minus 2 dimensional space, and it's really, conformally speaking, it's an SD minus 2. And these are stereographic coordinates. For that same SD minus 2. And I'll call this thing the celestial sphere. Because it is the celestial sphere if you're sitting at this point x. It's parameterized by the different directions that you can look out from the point x. So this is what we're doing. And normally right, so let me say, so now that we have an interpretation of these things as embedding coordinates, we should look at the homogeneity of our operators in Z, and that just comes from their spin. So this thing is lambda to the minus delta minus 1 times the same thing at x comma z. And that means that this thing transforms like a primary operator on the celestial sphere with dimension delta minus 1. So this OPE that we got from dimensional analysis should actually be consistent with conformal symmetry in the transverse plane in this RD minus 2. And these powers here are the usual powers that appear in the OP expansion, where we interpret this thing as the dimension of some operator type object in D minus 2 dimensions. Okay, so now I want to continue convincing you that this is weird. Here we're taking a product of these light transformed operators at the same point x. And normally in CFT you don't put operators at the same point. And the reason you don't do that is because for local operators there's a singularity at coincident points. But there doesn't necessarily have to be a singularity for non-local operators, and that's what we're studying. But there's a sort of interesting thing that happens, which is that if you really could put operators right on top of each other, then their dimensions would just add. In CFT, the dimensions of things in the OPE of two operators don't add because there's a singularity, there's some non-trivial x dependence as you bring them close. But if you could really just put them right on top of each other, their dimensions would add. And so it means that the dimension of this product is the sum of the dimensions of the constituents. So I'm going to assume for the rest of this lecture that this coincident limit actually is well defined, and it turns out to be well defined under not too strong conditions that you can ask me about afterwards. So what are these guys? Okay, so this is the light transform. So these are 1 minus J1 and 1 minus J2. Let me define J such that this thing has dimension 1 minus j. So we get some kind of selection rule. J equals j1 plus j2 minus 1. So this product looks something like a light transform of an operator with spin j1 plus j2 minus 1. But there's another symmetry that we should look at, and thankfully Tom introduced this symmetry already, which is CRT. So CRT is an anti-unitary symmetry, and when acting on local operators, it takes a local operator at points x and z to O dagger of x bar comma z bar, where this bar is the Rindler reflected position. So x bar is at minus x0, minus x1, then x2, and so on. Okay, so this is an antilinear map on the space of operators. But we can do something kind of silly to turn it into a linear map, which is to just take the Hermitian conjugate again. So if we take the Hermitian conjugate, of this whole thing, then we get a linear transformation on the space of operators. Because it's linear, it can have an eigenvalue. And so I'll leave this as an exercise. You can check for yourself that if we apply CRT to the light transform of some operator O, and then we Hermitian conjugate that, then we get back the same thing with a -1 to the j. Okay, so these light transformed operators have a nice eigenvalue under this operation, and I'll call this eigenvalue the signature of the operator. Oops. Okay, so here comes the weird thing. So let's study the signature of this product of light ray operators. So we take this whole thing and then take Hermitian conjugate. Okay, so it's not too hard to convince yourself that this is just equal to the signature of the sum of the signatures of the two, -1 to the j1 plus j2. And then this Hermitian conjugation reverses operator ordering. And for the purposes of today, I'm going to assume that these operators commute with each other. The rough argument being that they're being integrated along this null plane. They're space-like separated from each other, so you should expect that they commute. That turns out to be a little bit of a subtle question sometimes, but they do commute in a wide variety of situations. And so that means I'm just going to swap them. And so to summarize, this means that our product of operators, our product of light transformed operators, looks roughly like the light transform of a spin j1 plus j2 minus 1 operator with signature -1 to the j1 plus j2. So for example, if you had two Anak operators on the same null plane, then the product of Anak operators transforms like a spin 3 the light transform of a spin 3 operator with even signature. So in particular, these computations show that you could never get the right answer for this OPE by taking the OPE inside the integrals. Okay, you might have gone, oh, well, I have these two integrated operators along these null lines. Let's just take the OPE of the operators and then integrate that. And that would never produce the right answer because in the OPE, you'll always get operators whose signature coincides with their spin. And in fact, doing that, doing the OPE first before doing the integral is not valid because the integrals leave the regime of convergence of the OPE. Okay, so you can probably guess what the resolution to this is. The resolution is that it's not literally the light transform of a local operator that appears, but instead it's one of these funny light ray operators. And for these light ray operators, we get to choose independently the spin and the signature. So instead, so this is not really correct. Instead, we're going to get these light ray operators with different dimensions and a specific spin, j1 plus j2 minus 1, and signature equal to -1 to the J1 plus J2. So as an example, if we take two Anak operators on the same null plane, then the thing that appears are even signature spin-3 operators, which you can think of as what you get by taking the even spin operators and the even spin light ray operators and analytically continuing them to spin 3. The fact that something like this should be true was already pointed out a long time ago in a paper by Hoffman and Maldacena. They looked at some examples in n equals 4 super Yang-Mills theory at weak and strong coupling and saw that the leading term in the OPE was indeed described by some kind of funny even spin but spin 3 object. And what I want to do with my remaining time is just explain to you how to make this story completely rigorous using the tools that we've developed. Any questions? Yes?
Can you determine what's the OP coefficient in front?
That's what I'm going to talk about. Yeah. What's that?
Separating them in the minus direction, taking OP in the minus direction.
Separating them in the minus direction. Oh, yeah, that's a good question. So once you have these light ray objects, there are a whole big variety of different types of OPEs that you might consider. So here we're talking about a very particular OPE where I take them parallel, space like separated, and I move them like this. I mean, you could do some general position OPE and you understand. You're suggesting this. So yeah, you could absolutely try to study something like that. I think actually the techniques that I'll talk about would be useful for that. Yeah. Other questions?
But then if you go in the x minus axis, they don't start at the same point.
So it depends on what you're doing. So that's right. They don't start at the same point. But if you take a limit where they get to the same point, then I think it would amount to the same thing here. If you take different polarization vectors and you take their x minus as the same, then you're going to end up with the same picture that I'll derive, I think. Okay, other questions? Yeah.
So you said you can't do the OPE first and then integrate?
Yeah.
Does that mean that if I give you a correlator with, let's say, 2 Anaks and a bunch of other local operators, I take the integrals out, I first compute that correlation function exactly, and then I integrate, that I'll get the wrong answer?
No. That will be fine.
Ah,
so
okay.
if you can do the OPE and you're smart enough to resum the whole OPE, then you'll be fine.
Okay.
Yeah.
But
The
you
point
can't
is that
just-
you can't do it term by term.
Term by term, I see.
Yeah. Other questions? Okay. Great. So let me just describe to you how this goes. Basically what we're going to do is we're just going to prove the inversion formula again. Okay? So for those of you who really enjoyed that, you're lucky. It's going to happen again. Okay, so the first step was to consider a matrix element. So now we're going to look at a matrix element of this product of light transforms. Before we took a matrix element of a light ray operator and it was fixed by conformal invariance up to a coefficient. But now that doesn't quite work because this thing depends on too much data. So this depends on x3, x4, x, z1, and z2. So it depends on an extra polarization vector, an extra z. Before we can even get started, we need to project this thing onto irreducible representations. That is, we need to make it so that it only depends on the amount of data in a conformal three-point function. And the way to do that, one could potentially guess from these lectures if I had been infinitely clear, but I'm sure I haven't. But the thing that you should do is use harmonic analysis on the celestial sphere. So harmonic analysis is precisely the tool for picking out things that transform in specific ways under the conformal group. And here we have these 2 points on the celestial sphere, Z1 and Z2, and we want to merge them into a single point. And the way we merge things into a single point is by computing the partial wave using harmonic analysis. And so that's what we're going to do. So we're going to integrate Z1 and Z2 against a 3-point function on the celestial sphere. So I guess I'll just reuse my expression here. So we're going to take an integral d minus 2 Z1, d minus 2 Z2. This capital D, remember, is the funny measure in d minus 2 dimensions that I defined earlier. It gives us a way to do conformally invariant integrals over the celestial sphere. So here we have something that depends on 2 points, so we should merge them using a 3-point function on the celestial sphere. And I'll write that like this. So I'll introduce these fictitious objects that I'll call P. This is just silly notation for the unique conformally invariant object on the celestial sphere with these quantum numbers. So delta 1 minus 1, delta 2 minus 1, and delta minus 1, those are the dimensions in d minus 2 dimensions, the scaling dimensions. And then the tilde means I should take the d minus 2 dimensional shadow of this. So overall, this is something that has dimension d minus 2 minus delta 1 minus 1. The reason that's good is because then, so this thing has some homogeneity in Z1, this thing has some homogeneity in Z1, and the measure does too, and together they give something with homogeneity 0 in Z1 that can therefore be integrated in a well-defined way. So, and by the way, this is kind of abstract notation for something pretty concrete. So it's an embedding space 3-point function on the celestial sphere. And the way you make 3-point functions is you take products of dot products of embedding space vectors raised to powers. So this is something like this to some power minus 2 z1 dot z to some power minus 2 z2 dot z to some power, where the powers are determined by these dimensions appearing here. So this is what I would call the partial wave on the celestial sphere. And it basically just is replacing Z1 and Z2 with a single Z. And the reason this is nice is because it encodes in it the information about all the objects appearing in the OPE of these two guys on the celestial sphere, which is what we want. So that's one reason it's nice. And then the other reason that it's nice is that it's now fixed by conformal invariance. We got rid of one of the z's. Now we have 3 x's and a single z. And so that is now fixed by conformal invariance. There's some coefficient, which is dynamical, that's not fixed by conformal invariance. And then this whole thing has to transform like a 3-point function with the following quantum numbers. So one of the things here is going to be like the light transform of an operator with dimension delta. So that's why I picked this particular thing here. This ensures that this whole thing has homogeneity 1 minus delta in z. And that is the right homogeneity for the light transform of something with dimension delta. And then our funny spin from the selection rule is going to show up here. Spin j1 plus j2 minus 1 of x and z, O3, like that. Okay? So the claim is that because this is a conformally invariant integral on the celestial sphere, this whole thing just transforms exactly like this. So it's fixed by conformal invariance up to this coefficient. And now we'd like to determine this coefficient. Okay, so the next step is to use the fact that the light transform here kills the vacuum. So before we had an argument for getting the double commutator and proving the inversion formula, and now this part's going to be way simpler. The light transform kills the vacuum, so we can immediately do this. And now we're in maybe a more familiar situation. We have some thing that we'd like to compute, some dynamical function times a conformal three-point function is equal to the integral of some kind of kernel against the double commutator. And this was a penultimate step in the proof of the inversion formula. And so the way the final steps go is that you find some dual object, some object that you can pair with this thing under this Lorentzian invariant pairing, something that pairs to 1 with this thing, and that lets you write a formula for this. You take the pairing of both sides, and you end up with the integral of the double discontinuity, the double commutator, against some kind of kernel. You massage the kernel and write it as a conformal block. So the argument for writing it as a conformal block proceeds in the same way as before. You show that it's conformally invariant. You show that it's an eigenfunction of the Casimir, and then you determine its OPE limit. At the end of the day, what you get is that A of delta is equal to the integral of the double commutator against a conformal block, which is G sub J1 plus J2 minus 1 plus D minus 1, comma, delta minus D plus 1. It's a special case of the conformal block appearing in the inversion formula. And this tells you that A of delta is related to C of delta J. And there's minus I pi out front. So that answers your question of what the OP coefficient is. It's minus I pi. So the fact that the same conformal block shows up implies that these coefficients are related to each other. This is minus I pi times C plus delta J1 plus J2 minus 1. Yeah, I guess we get C plus minus, where plus minus is equal to minus 1 to J1 plus J2. And so then you can upgrade this to an operator statement. Now you know all the matrix elements of these products of light transforms are related to the matrix elements of the light ray operators that we described before. And so you can write a final formula for their OPE. Which says that, so this A of delta was the coefficient in the partial waves with respect to Z1 and Z2. So to get back the original thing, we have to integrate over delta. And then here's our light ray operator. This thing is an OPE differential operator in d minus 2 dimensions. And to be more explicit about it, it's easier to write it in terms of the y variables, the transverse directions, instead of the embedding space variable, z. So this thing, in terms of y, this is our y12 to a power, delta minus 1 minus delta 1 minus 1 minus delta 2 minus 1 times 1 plus derivatives with respect to y plus dot dot dot. So hopefully you're familiar with the usual OPE in Euclidean signature. When you take an OPE of two operators, you get the contribution of the primary and then an infinite sum of descendant contributions. And so that's what this differential operator represents. So the idea is that with respect to the celestial sphere, these light ray operators are the primaries appearing in the OPE of these light ray operators. Yes?
Can you explain why the OPE coefficient is fixed to be I pi and not some sort of dynamical information?
Yeah. So that's a great question. It's because the dynamical information is hidden in here. So let me remind you what the matrix elements of those things look like, or what the properties of these things are. So the idea is that the residue at delta equals delta star of these funny light ray operators is equal to F12 O star times L of O star. So where this is at integer j. So where 1 and 2 are the operators that you use to build this thing. So really, strictly speaking, I should have been writing some extra indices. These light ray operators depend on the things that you use to build them. And they contain the OPE coefficients of these things. So this somehow contains the analytic continuation of this OPE data. In this formula, what you really have is minus I pi times the analytic continuation of the OPE data contained in this thing, which are just the OPE coefficients 1, 2, and then O star. So the formulas make it a little hard to parse what's going on, but the statement is that if you want to know the OPE coefficients appearing in this thing, you should take the OPE coefficients appearing in the usual OPE and continue them to spin J1 plus J2 minus 1. Yes?
You took OPE in the transverse direction. Can you talk a bit about now evolution in the transverse direction?
Evolution in the transverse direction? What kind of evolution?
Usually when I take the 4-point function and OPE decompose it, I take OPE of 2 and then evolve the rest. It would be the analog here. What is the... When I evolve the rest, it's the dilatation operator for standard OPE.
Well, okay, so the claim here is that there exists an OPE that looks very much like the standard one in the transverse plane. If you had a bunch of these guys on the transverse plane, then you could pair them up and do this OPE. And perhaps you could keep repeating the OPE. So that I'm not sure, because this computation was just about what happens if you take an OPE of light transforms of local operators. But there's a more general question of what happens if you take OPEs of these guys with each other. And that we don't know. But there's a very natural guess that you just get the same light ray operators back.
Yeah, but there should be something that on the sphere should become like dilatation.
That's what we're doing here. We're diagonalizing the dilatation on the celestial sphere. So the dilatation on the celestial sphere is a boost with respect to usual space. This is the fact that if you boost, then the light rays go like that. They're being compressed towards a point. So that's the generator that we're diagonalizing.
So then, to actually get back to the sum
Yeah, good. Okay, thank you. Yeah, so I almost didn't say that. So yeah, that's right. So the way to get back to a sum is by using this manipulation from the first lecture, where in harmonic analysis you naturally get these integrals over a principal series. I didn't even write the principal series here. So this is over d over 2 minus I infinity, d over 2 plus I infinity. What's that? No, because I defined delta in such a way that it's the usual principal series. And then, yeah, and so then you take this thing and you deform the contour and you pick up the poles. After doing that, you end up with a discrete sum. You end up with a discrete sum under the assumption that that this thing as a function of delta has only simple poles on the real axis. And we know that's a true fact for integer spins where the integer matches the signature. We don't know if that's true where the spin doesn't match the signature. So that's an open question. But either way, you get an expression. You can deform the contour and get an expression for this as some kind of sum over the singularities of this thing in the delta plane. Yeah.
So to what extent can we think that there's really some kind of physical CFT, 2D CFT that lives on the celestial sphere encoding all of this?
Yeah, that's a really interesting question. So I don't think there's I don't think this is holography squared. I don't think there's a 2D CFT, a local 2D CFT. But there is something kind of surprising going on, which is that it wasn't obvious that an OPE should exist at all in the first place. So let me remind you of the usual argument for the existence of the operator product expansion. It's this beautiful argument that you can find in Polchinski. Let's say we take two operators in some Euclidean path integral. We take these two operators. Let's suppose all other operators are far away. We can draw a sphere around these two operators and do the path integral over the interior of the sphere. And that produces some state on the boundary of the sphere. So it produces some state psi in radial quantization. And then we just expand psi in eigenstates of the dilatation operator. But those eigenstates of the dilatation operator are precisely the local operators of the theory. So it's like a pretty trivial statement in this case, the existence of the OPE, and it just comes from cutting the path integral in the right way. In this situation, there's nothing like that. You have these null lines on the null plane, and so like where do you cut the path integral? There's no sphere that you can cut it around. So there's no obvious Hilbert space interpretation of this OPE. So it wasn't obvious at all that, at least to me, it wasn't obvious that there should exist any kind of OPE that's like a discrete sum over contributions. Yet there is. And it's indicative that perhaps there's some better way of getting at this that bypasses this complicated mathematical machinery and gets to an argument that looks more like this. Some kind of Hilbert space interpretation of these null line operators. I think that would be really interesting, but I don't know what it is. Yes.
Do you know any connection to Reggie?
Good. Okay. So this is one application of these light ray operators, and the other another application is conformal Reggie theory, that I didn't have time to talk about. But you can write, so if you take a 4-point function and you study it in the Reggie limit, you can rewrite it as in such a way that you see that the Reggie limit is controlled by a sum of these light ray operators. It's just a rewriting of the way we already know how to do conformal Reggie theory, but it gives an interpretation of the objects controlling the expansion. So yeah, maybe for the benefit of the others here, it would be useful for me to just make a plot sort of summarizing this situation. So again, this is this Chu-Fauci plot of the spectrum of a CFT. We have analyticity and spin, so we have these trajectories. And the claim here is that, okay, and so then we have the, now we know light transforms of local operators are here. They're integer points on these trajectories. So for example, here's spin 2. This is the stress tensor. Here's spin 4. And the claim is that the way you get the light ray OPE, let's say we're studying the light ray OPE of two Anak operators, so L of t, is you take this Chu-Fauci plot and you cut it through at spin 3. And then the things appearing in the light ray OPE are these guys. Reggie theory is about a different place on this plot. It's about this region down here. And you can rewrite conformal Reggie theory in such a way that you see that the light ray operators in this regime are the things that control the expansion in the Reggie limit. Thanks. And let's all thank the organizers of this wonderful school.